continue with partial pivoting and finish up all the factorization, then do a little bit of triangular solve and figure out how you can actually solve linear systems of equations once you obtain the triangular factors. And if we finish that, I think the next section will be door factorization, which will bring us to the end of dense linear algebra. And after that, we'll start studying sparse problems. Okay, so first let me slide. So let me just talk briefly about what partial pivoting is and why we might want to do it. So you might consider in general that we've done some part of the factorization, and we are now trying to figure out the next row we want to operate on. So we want to usually take this row, scale it by the appropriate elements of the column, and subtract it out when scaled by this factor. So we don't want, and so the scale will be equals if this is something like a 7, 3, and this is a 3, 3. The scale will be a 7, 3 divided by a 3. So essentially, the scaling factor will be large if this entry is larger than this entry. So that will potentially mean that what we have in the trailing matrix may grow substantially with respect to the size of the original elements. So we took some elements from this row and we scaled them by a large factor. And so numerically, that can make us unhappy if throughout the execution of our algorithm, the magnitude of the values we operate on is changing significantly, because it may mean that the roundup error we incur for those numbers will lead to greater relative error in the final output. So for this reason, we often want to make sure that this diagonal element by which we divide within LU is large. So to do so, we can do, and most often will do, row pivoting, which is called partial pivoting, where we select the max AI3 here if this is the third column, and so let's maybe say that this is the I that corresponds to the maximum row, and we then rotate or swap these two rows and proceed with the factorization. So to do so, there are two overheads we discussed last time. One is the computation of the max element. So this requires effectively a reduction over this row, over this column, to figure out who the maximum guy is. The other is the fact that you have to take a whole row and to rotate it elsewhere into your matrix, which is a somewhat irregular axis pattern and potentially requires data movement. And you will have to effectively move every row like this on average once throughout the algorithm, so it's something that you really want to avoid. Okay, there is, of course, other types of pivoting as well. So one that you might learn in a numerical linear algebra course is complete pivoting, where you select essentially both the row and the column and pivot them so that this entry is effectively the maximum magnitude in their entire trailing matrix. And this actually gives you guarantees of stability, unlike partial pivoting. But partial pivoting is very, very robust in practice. So complete pivoting requires only more kind of communication, and it's even harder to do the partial pivoting. That's why it's usually not done even in sequential algorithms. So we'll now talk a little bit about kind of alternative methods one can do for pivoting, only at a high level, but to make sure you guys are aware that these exist. And there's also some common patterns within them that we'll see in other communication effective algorithms. So the basic problem, and it's a problem that we'll face also in other matrix factorizations and numerical algorithms, is that within the panel we have some part that requires kind of global communication. So we have some coupling here that is non-local, that prevents us from effectively parallelizing the panel factorizations so that they're decoupled. So we need to do something smarter there, or we need to figure out a way to pivot that's somehow local to blocks. So this just, yeah, I think I've basically covered all of this. So if we tried to do partial pivoting within our 2D algorithm, the basic overhead, it's a pain to do the row rotations, but if you're smart about how you do that, they don't really dominate your cost. I'm not going to try to describe how. But the most basic problem is that if you have everything partitioned, then computing this max involves communication, and it involves essentially a reduction for every column. So we pick up a latency term that looks like that. So S is our latency cost measure. This is what grows in particular. So one way to get around this is using a 1D algorithm, but then we are stuck at the communication efficiency of 1D algorithms that are quite a lot lower. They're also less concurrent. Okay. So some of the alternatives that we can then use involve, and probably the most promising one is called tournament pivoting. And so I think I'll try to describe this one in a little bit of detail and not do many of the others. So tournament pivoting, the setting is basically that you work on a tall and skinny matrix. And so this tall and skinny matrix may be a panel over a matrix, or may just be the whole LU factorization. And what we'd like to do is compute the entire pivot matrix all at once without actually doing the LU factorization. So then we can pivot just one time and do the LU factorization independently with processors only communicating a small number of times. And I should make this actually a little more tall and skinny to demonstrate the point. So if we have a lot of processors, we'd like to compute an LU factorization like this. The panel might be partitioned somehow like that. And so we don't want to have to send and do a reduction for every one of the columns. We'd like to try to do things bulk synchronously. So if we call these blocks A1, A2, A3, A4, don't forget about the last block because they're like powers of 2. What we'll do is actually try to do first partial pivoting LU within each block. So you would compute factorizations like this. Then you would, instead of trying to operate on these L's and U's, actually try to figure out what are the rows that in each one of these did we pivot to the top. So in particular, we'll look at P4, A4. So we'll apply this permutation matrix to A4, which looks like a matrix like this. And then we'll say that this is A4 bar, the top part of A4. So where this is n by n, and this is n by n. So we select the rows that we pivoted up from this last factorization. Then we do same thing here. So we take the top row selected here. And then we do a tree that combines these. So we then compute the LU factorization of a matrix that looks like this. And we do so with partial pivoting. So now we get some new matrix out of which we again extract the rows that we pivoted. So we'll pass up the top part of something like that. So what we're effectively doing is building a binary tree of kind of pivot factorizations, which will overall be of height number of processors. And so what we'll end up with at the end is some amount of rows of A that have been selected throughout this tournament. So at every kind of step, at every node in the tournament, we've had two sets of rows compete against each other, and out of them we selected a set of winners. And so the final set of winners at the end of the tournament tree will be the final pivot rows that we'll actually use on the original matrix. So we can then combine these tree of pivots and put the rows that we'd like to the top of the LU factorization. So in effect, we're actually doing some extra work here. So where is the extra computation here coming from? So first we need to figure out the pivot rows, then once we have those, we'll put them up and perform a full LU factorization. So with respect to just doing a LU factorization with partial pivoting sequentially, what amount of extra computation do we need to do? Where does it come from? So these LUs, right, which happen for the tournament tree, are extra work, which are just being used to select the final pivot rows. And then we're just discarding these LU factors. So we'll actually go back and recompute a whole LU factorization again. But this tree of factorizations is purely overhead. The tree costs about as much as an LU factorization itself. So the algorithm effectively doubles the cost of doing an LU factorization in terms of work, but brings the number of messages you need, your latency cost, from something proportional to the number of columns to something proportional to just log p. So you select those pivot rows once, and you can do the whole skinny LU factorization after that with just a single broadcast. So in effect, it changes the algorithm to reduce its depth from something proportional number of columns to something logarithmic in the problem size, which is in general kind of a common theme that you might see in parallel algorithms. You adapt some different numerical structure, so you actually reduce the amount of dependencies involved, and you can still proceed. So if you do the analysis for what happens in terms of stability for this scheme, it is not much worse than partial pivoting. There you can prove theoretical bounds on the pivot growth, which for LU are already exponential in problem size. Here they are like somewhat doubly exponential, I guess. But in practice, you see actually very good behavior. And one of the reasons it doesn't really incur more error is that when you pass up things throughout the tournament, you always pass up the rows of A. You don't pass up these LNU factors. So the LNU factors you computed may not be make it potentially aggregate error, but these rows of A don't really. Okay. So another strategy that is to an extent simpler but much less powerful formally is trying to essentially only do a pivoting that's non-local, so that goes outside of your block, if you know that there's some much larger pivot element to be found. So effectively, if you have a good row locally, if it's within some threshold, you just pivot that and you avoid communication. But there is, I think, not all that much you can say formally about how this will behave. I think threshold pivoting comes from actually sparse factorizations, which we'll get to in some detail eventually, where we want to potentially avoid pivoting or decide when to pivot also while considering the amount of computation we have to do and the sparsity of the matrix. So there, a pivot may change the fill structure of your algorithm, and you may want to kind of consider how much numerical accuracy will really be worth. So this idea of threshold pivoting came from there. A different approach that's somewhat, I think, more prominent, at least in threshold pivoting, is pairwise pivoting. And so with pairwise pivoting, we will really think of LU as eliminating a single entry at a time. So I believe this is also how Gaussian elimination is often taught in linear algebra courses, is as doing a single rotation to introduce one non-zero at a time. So one usually starts in the lower part and considers essentially applying a 2x2 matrix to these two rows, so as to introduce a 0 there. And so one can do so without kind of considering the permutation of these rows, but one can also consider permuting them as well. And so that defines a different space of little 2x2 transformation matrices. Now you can embed these little row-wise transformations into larger matrices, where this is basically the identity, and this is just acting on the last two columns. So we might call this thing L1, and then we'll actually here then do a bunch of transformations, L2 to LM, that eliminate other entries. So overall, we'll need something like n times n minus 1 over 2 transformations to introduce a 0 to every one of the lower diagonal entries. Then effectively, our L factor overall will have the form, so it's as the product of all of these. So you can then effectively also build in pivoting into this by restricting essentially pivoting to something that only happens as a transformation to these two rows. And this can also be shown to be stable in practice. It's certainly different, and you're really kind of pivoting as you're doing LU factorization. So what you actually get in terms of these matrices is a little bit of a mess. So each one of those corresponds to doing some permutations, or a permutation and an elimination of some particular non-zero. But you can often take this whole form that you computed and apply it in the same way as you computed it. So just like you would permute two rows and take some kind of scalar multiple of the one and add it to the other, if you want to actually compute the inverse of this, or to apply it to some, as part of a solved in a triangular system, you can invert each one of these individually and apply them. And those just correspond to rescaling pairs of rows. So it's just like in LU factorization, you can think of it as a bunch of row transformations that you can then apply in your forward and backward solves as you go along. Okay, so I won't talk into much detail about this steps of pivoting, but this does result, if you analyze LU with pairwise pivoting, in an algorithm that is effectively communication optimal. So it's as good as anything else. The same is true for tournament pivoting, but the algorithms are very different. Okay, yeah, so and all of these have some trade-off. None of them are quite as stable as partial pivoting, but these two are theoretically and practically close, so they're practical. The exact trade-off of which one is actually better or which one should be used, I would say, is still a problem. So there's kind of fairly recent papers analyzing both of these. Okay, so I think, yeah, and then as I mentioned yesterday, if you're really worried about stability and you don't like the overhead of these pivoting strategies, you may be tempted to do QR factorization. There's also other reasons you may want to do QR factorizations, and not all the many fundamental reasons not to. So in a sense, it's a little bit more powerful. Okay, any questions about LU or LU with pivoting? Yeah, the pivoting we kind of did at a high level. I guess as a final thing, image simplification, we discussed these algorithms that could achieve essentially perfect strong scaling up to some extent by trading off memory and communication. That's possible to reduce the communication cost of LU factorization in a similar way, and also LU with pivoting, but it's not quite as much of a free lunch. It comes at a cost of a higher latency term. But I won't really cover those algorithms in any detail. they basically also tried to do a 3D partitioning rather than a 2D partitioning, but run into more problems